Okay, so now that you know what an acid and a base is, we are going to discuss the different types of acids and bases. And essentially this is how over time our definition of an acid and base has changed. So there's 3 different classifications you want to be familiar with: Arrhenius, Bronsted-Lowry, and Lewis acids and bases. So the oldest definition of an acid and base was from the late 1800s with Svante Arrhenius. He defined an acid as anything that gives off a proton, an H+. Right? So another way you may see that is an H+ that equals a proton. Because when hydrogen has 1 electron and 1 proton, when it forms an ion, it gives away that electron, so all that's left is a proton. So that's why we call it a proton. And then bases give off OHs. Right? So that makes these relatively easy to identify based on their formulas. Right? So your acids are all going to have, H's attached to some sort of negative ion, like chlorine or oxygen, or let's see, acetic acid, that's an acetate ion. Right? So you're going to have a positive H attached to a negative ion. And your bases are all going to have OH in the formula. All right? So like sodium hydroxide, potassium hydroxide. OH minus, the name of that is hydroxide. All right? So this is where that whole neutralization reaction came from, because something is giving away an H+, something else is giving away an OH-, and then when you combine those together, that's how you get your water. All right? So if you recall from our last lesson, neutralization reactions occur when an acid and a base react together to essentially cancel each other out. All right, so we call those neutralization reactions. And when those happen, you always make a salt and water, or H2O. All right, so we've got you can see in here, we've got our OH and our H+, and that's how we get that H2O. So, something you should be able to do is, given a list of chemicals, be able to pick out the Arrhenius acid or the Arrhenius base. So see if you can give it a shot here. Of these choices, which is going to be most able to give off that H+. It's going to be your HCl. Then of your base choices, which of those is going to have that OH- in its formula to give away? All right. Key is they should be attached to each other. All right, so that way you have that clear hydroxide in there. Now, the problem with Arrhenius's definition is that it didn't cover everything that we know actually can be an acid or a base. For example, ammonia, which has a formula of NH3, is actually a base. All right, so even though based on its formula having all those H's, you would think that might be an acid, but in actuality, it's slimy. It reacts with acids, right? So somebody had to come up with a different way of classifying acids and bases to account for examples like this. So the people who came up with the first iteration of accounting for ammonia-type bases were Bronsted and Lowry. So this is where you get those Bronsted-Lowry acids and bases. All right, Bronsted-Lowry. All right, and really the Bronsted should have the little slash through it because it's a nice German name, but not every, you'll see this in your text as well, not everything has the ability to put that in there. So the difference with Bronsted-Lowry acids and bases is that we identify acids as anything that donates a proton, all right? Instead of just having a proton in its formula, it's going to give away a proton. And then really the big difference is that a base is anything that is then going to go and accept that proton. All right. So this means a lot of times you will actually have water. So Bronsted-Lowry's definition of acids and bases actually makes it so that water can act both ways. It also makes it so that you don't necessarily have to see the H plus or see the OH minus directly in your formula. All right. So, but this is a really, really unique ability of water is based on the Bronsted-Lowry definition, it can go both ways. All right. So, for example, when you are dealing with ammonia, all right, ammonia is your base. It's going to accept a proton. Water is your acid. That's what's going to give up that proton. All right, so you're going to have a proton that goes from water to the ammonia so that afterwards you have an OH minus, all right, and then the NH4 plus. Likewise, you can also have water act as the base, right? So if you have a typical Arrhenius acid, it will react with water. Again, you're going to have an H plus going from your acid to your base, and that's going to create a unique or a new compound that you want to be familiar with, the hydronium ion. So when water accepts a proton or acts as a base, all right, that's when you form this hydronium ion. And the hydronium ion is H3O plus because it has that extra hydrogen on it. So that's a good thing to write down there. So another thing related to Bronsted-Lowry that you want to be familiar with is the relationship between your reactants and your products. All right, in the sense that whatever your base was in the reactant, afterwards it is going to be a conjugate acid. All right, so your ammonia, right, after it picks up that H plus, it is now a conjugate acid, which means ammonia can give away a proton in a future reaction. All right, likewise, the acid in your reactants, all right, so the water, afterwards, it can act as a base, or the OH minus that results after the water gives away its proton, all right, it's a conjugate base and can accept an H plus in the future. All right, so this is a relationship that you want to remember and kind of wrap your head around. All right, so just keep in mind what's going on here is really what it acts as in the beginning. It becomes the opposite with the word conjugate in front in the end. All right, so make sure you recognize that relationship here because that's something you will get asked questions about. The last variation, and this is the most recent one, steps away from using the term proton and talks more about electrons. All right, so acids, if you think about it, if they were given away a positive proton, all right, what's going on is we've got an electron that we're gaining. All right, so acids accept electrons, bases donate electrons. If you really want a simple, just kind of table to write down to help you remember these things, all right, so according to Arrhenius, acids form H pluses. Bronsted-Lowry says that that's actually donating a proton. And then finally, Lewis, the most recent definition, says that that is accepting an electron pair, right? Whereas bases, on the other hand, go from forming an OH minus to accepting a proton to donating an electron. All right, so this is a good table to probably screenshot or something so that you can use this when you run into multiple choice questions like the one you're about to see.